Okay, yeah. Yeah, we will be dealing with semiconductors. Already we have studied what is semiconductors. I'll be briefing all the topics which we have covered up so far. Okay, we have three materials which are called as an insulators. The one is insulators, and the one is conductors, and the one new what we are studying is now semiconductors. We'll be studying the energy band diagram for the insulators, semiconductors and the conductors, and we will see what the materials, how the materials are differ with each of these parameters. If you see in the case of insulators, suppose this is a valence band and this is a conduction band. The gap between valence band and conduction band is called as an forbidden energy gap. Forbidden, not allowed. Forbidden in the sense not allowed. Forbidden energy gap. So in the case of insulator, the gap between these two bands is very large. This gap is very large. So even if with respect to thermal excitation or any kind of energy, if you try to push one valence electron to the conduction band, it will not go because the gap is much higher. And how we can say what is valence band? The valence electrons, the electrons which are rotating in its outermost shell are called as in valence electrons. Because these electrons are in its outermost shell, it is very loosely bound with the nuclei. So if you give an energy, this particular electron can become free and it will place to the conduction band. And these free electrons which are present in the conduction band are responsible for the flow of current in the circuit. Okay, so here the gap is much higher in the case of insulator. If you see in the case of conductors, if I draw a valence band, and this will be a conduction band. So in the case of conductors, these valence band and conduction band overlap with each other. So they are readily available in the case of conductor. What the best example for this is copper, what we normally study, copper or aluminum, isn't it? So here this is the two bands are overlapping with each other in the case of conductors. So what is now semiconductors? Semiconductors in the sense the materials whose resistivity falls in between insulators and conductors are called semiconductors. The same semiconductors will be acting at a different temperature as an insulator or as a conductor. So if you see energy band diagram with respect to semiconductor, this is a valence band and this is a conduction band. It means the gap between these two is very small. This here it is large. So at room temperature, the semiconductor material will act as an insulator. The same semiconductor material at a higher temperature, it will act as an conductor. And the resistivity of this semiconductor is from 10 to power of minus 4 to 0.5 ohm meter. It's a resistivity value. So we can define again a material whose resistivity falls from 10 to power of minus 4 to 0.5 ohm meter are called as an semiconductors. Got it? Next, semiconductors again are of, if you classify this, these are of, again of two types. One can be called as an pure and the other is called as an impure. Pure and impure. So what is pure? Pure in the sense the number of holes and the number of electrons are equal. When the number of holes and number of electrons are equal, then that can be called as an pure semiconductor. Impure semiconductor, this can be called as an intrinsic or pure intrinsic semiconductor, or this can be called as an extrinsic semiconductor. Intrinsic semiconductor, number of holes and number of electrons are equal. It is in the pure form. But whereas in the extrinsic semiconductor, again there are two types. They are called as an One is called as an p-type semiconductor and the other is called as an n-type semiconductor. Now we are introducing with a new kind of semiconductors which is called as an p-type and n-type. So what is p-type? What is p-type? When we take a small amount of trivalent impurity and add it to a pure semiconductor, then a material which is formed, that crystal is formed, it's called as an p-type semiconductor. If you see an example of trivalent, if I take an arsenic and any arsenic, yes, and if it is added with a gallium or indium or silicon, suppose I say silicon is the best example of semiconductor, and if I pair a covalent bonding, this is how it happens. So silicon have a 4 valence electrons, so this is how the bonding will take place. This is how the bonding will take place. Oh. This is just a picture of bonding, covalent bonding. So arsenic have, because it's a trivalent impurity, the valence electrons for this particular element is 3. So we can't have a bonding for this particular electron. So it means there is a vacancy, and this vacancy can be called as an vacancy or can be called as an hole. It means if the majority charge carriers in that particular crystal material are holes, then it is called as an p-type semiconductor. It means when a trivalent impurity is added to a pure semiconductor, then the crystal which is formed, it is called as a p-type semiconductor. Similarly, if I take a pentavalent impurity which have a 5 valence electrons, example boron, if I take a pentavalent impurity and it's added with bonded with a pure semiconductor, then because of 5 valence electrons, 1 electron will be excess, and which is which can be donated to other bonding. So here in the case of, if I say that the majority charge carriers are electrons, then that particular device or that particular material can be called as an n-type semiconductor. This is how p-type semiconductor and n-type semiconductor are formed. This is n-type semiconductor. This is p-type semiconductor. So simply we can say that the majority charge carriers are holes in the case of p-type, and the majority charge carriers are electrons in the case of n-type. Now what is p-n diode? What is p-n diode? When p-type material and n-type material are suitably added, then that crystal is formed, which can be called as a junction diode or which can be called as a p-n junction diode. The symbolic representation for p-n diode is in this form. This is p-type positive and this is n-type negative. This can be called as, this is anode and this is cathode. When p-type material and n-type material are suitably formed or suitably in the process of crystallization, then the particular material which we get it is called as an p-n junction diode or junction diode. Okay, now we will see the working of this particular p-n junction diode, which can be formed into 2 bias. One can be called as a forward bias, the other is called as a reverse bias. Let's see the forward bias here. This is forward bias, and here we will see the reverse bias. This is how we can draw. This is a depletion layer, this is p-type and this is n-type, and here this is a battery which I have connected. This is a plus polarity and minus polarity. Similarly here I am drawing at the same time the reverse bias also. This is a depletion layer, and this I have drawn minus, and here it is plus, and this manner this is minus and this is plus. Already we have seen in the case of p-type material the majority charge carriers are holes. In the n-type the majority charge carriers are electrons. Now the mode of connection is in this manner. I have connected a battery in this manner. The positive polarity of the battery is connected to p-type and negative is connected to n-type. So what will happen? Because this is a positive polarity, these are positively charged carriers, this will repel and this all holes will move towards the potential barrier or a junction barrier. Similarly, these are negatively charged carriers and this is a negative polarity. This will again repel and move towards the depletion layer or a junction barrier. And finally what will happen, all the holes and electrons which are moving towards the junction will cancel that potential barrier, and slowly we can see that if I connect an ammeter and milliammeter, slowly I can see that the current is flowing in the circuit. So this is called forward bias. The definition for forward bias, I can say that when an external energy is connected in such a manner which cancels the potential barrier and allows the current to flow in the circuit, can be called as a forward bias. To connect the particular diode into forward bias, the construction should be like positive polarity of the battery should be connected to p-type and negative should be connected to n-type. Similarly, if I see the reverse bias, the majority charge carriers are in the case of p-type are holes and these are again electrons. So what will happen, I have connected to the p-type material negative polarity, and here for the n-type material I have connected the positive polarity. Because both are opposite in, so the positively charged carriers will be attracting and move towards the negative polarity because it is opposite, so it will attract. So this will be moving away from the junction. This will be moving away from the junction. This makes the depletion layer in the sense the layer which doesn't have any mobile charge carriers, neither plus or minus. So here in the case of reverse bias, this depletion layer will increase, but because of the minority charge carriers present in p-type and n-type, there will be a small amount of current still flowing in the circuit, and which can be measured by a microammeter in the circuit. So if somebody asks how the current is still flowing in the case of reverse bias, that is because of the minority charge carriers. The holes are here majority, but minority carriers are electrons. So these electrons, because this is negative and these are negative, so this will be moving towards the junction. And similarly there will be a few holes which are present in the n-type, so this will be moving towards the junction. So because of the minority charge carriers present in the p-n junction, there will be a small amount of current, and that's the reason we have taken as a microamp. This is micro in the sense 10 to the power of minus 6 and milli in the sense 10 to the power of minus 3. This is how the p-n junction diode works in the forward bias and reverse bias. If I see the VI characteristics, the graph if I need to plot, it will be in this form. This is V, this is I, this will be minus V, and this is I. So if I see the forward bias, as we have seen earlier into the previous page, there was, unless and until both the holes and electrons cancel the potential barrier, there won't be any current in the circuit. So if I see the V value, V and I up to certain value, it will be 0, there won't be any current in the circuit, and then the current will be shoot up. So this is called a knee voltage, where the current have started rising. So for every material like silicon or germanium, for silicon it will be 1.1 volt, and for germanium it will be 0.3 volt. Unless you cross that particular barrier, the current will not flow into the circuit. So this is all about forward bias. If you see the reverse bias, again this will be in this form. Minus V versus minus I, we have taken it in the third quadrant, and this is called as a breakdown voltage. This is knee voltage, and that is the breakdown voltage. Got it? Okay. Next. Zener. Zener diode. Symbolic representation will be in this form. It's as simple as similar to the p-n junction diode, only it will be in the form of Z, and this will be p-type, this will be n-type, plus minus, anode and cathode. Diode, Zener diode, di in the sense di, one is cathode, one is anode, two, electrode, anode and cathode. One will generate the electrons, the other will collect the electrons. That's the role of actually anode and cathode. So Zener diode, as we explained earlier, if I see directly the VI characteristics, the only difference is the Zener diode in the case of, if I connect the Zener diode in forward bias, it will be similar and it will act same as an PN junction diode. So there is no meaning connecting Zener diode in forward bias. The special feature of Zener diode is only when it is connected in reverse bias. It is connected in reverse bias. If I see this V versus I, Zener diode connected in reverse bias in the third quadrant, minus V versus minus I, the graph will be like this. So this is called knee voltage and this is called breakdown voltage. But here if I see, it is a sharp breakdown. So when we get a sharp breakdown voltage, then that particular material can be called as a Zener diode. So a diode which have a sharp breakdown is called as a Zener diode. So here we can say that there is a constant voltage. So what normally we use in a stabilizer, instead of any fluctuation 220 to 290 voltage, this will ensure that there is a constant voltage given to our home appliances which will not damage our instruments. So the Zener diode application can be called as a voltage regulator. It regulates the voltage, it makes the constant voltage. The application of Zener diode is, it's a voltage regulator. A small note on the rectifiers. Morning I have told what is rectifiers, what it makes, which converts AC to DC. Once again I'm just drawing a principle of transformer. This is a primary coil, this is a symbol of transformer, this is primary coil and this is secondary coil. So whatever the AC supply I have given to the primary coil, surrounding to this coil there will be a varying magnetic field according to the Faraday's law, and this particular varying magnetic field zone I have placed one more coil which is called as a secondary coil, and here there will be a induced current in the circuit because of the Faraday's law, vice versa. If there is a varying current, there will be a magnetic field. If there is a magnetic field around the coil, then there will be a current flowing in the circuit. This is what the Faraday has told. There are two things into this. So here if I say that the 240 is a input voltage, if the number of turns in the case of secondary coil is less, and if I say that there is an output of 6 voltage, so it is making step down transformer. For this 6 voltage, if I connect a one diode and a load resistance, and if I measure an output across this load resistance, then this will make the 6 voltage AC into a 6 voltage DC. So this is called as an half wave rectifier. If I see the input, this is what the AC is, okay, and in the case of this half wave rectifier, if I calibrate this, so for the first half positive half cycle there will be a current in the circuit. For the next negative half cycle there won't be any current in the circuit. Again for the first positive half cycle there will be current in the circuit. So this is called as a half wave rectifier. How it happens? Already we have known the transformer, like 240 voltage is converted to 6 voltage. 6 voltage in the current is flowing. Once this particular, suppose I say these are the 2 points called as an A point and B point. So for the first positive half cycle, the point A become positive and the point B become negative. For the first positive, this is positive and negative. And if I see that the positive of the voltage is connected to the P type and this negative is connected to the N type. This is P type and N type. This is anode and cathode. It means the diode is in, if the positive polarity of the battery is connected to P type and negative is connected to N type, the diode is in which bias? It is in forward bias. If the diode is in forward bias, there will be current in the circuit. So there will be, for the first positive half cycle, there is a current in the circuit. But what happens for the first negative half cycle? This is first positive half cycle, first negative half cycle. Second positive half cycle, second negative half cycle. So for the first negative half cycle, this will become minus and this will become plus. The point A will become minus and this point B will become plus. So here if you see, minus is connected to P type and positive is connected to N type. It means the diode is called as a non-conducting stage, or it is into reverse bias. Reverse bias, though we say that the very small amount of current is flowing because of the minority charge carriers, that can be neglected. So here if you see that for the first negative half cycle, there is no current at the output. So only you got an output when you have a positive half cycle only. For every negative half cycle, there is no output. So this is called as half wave rectifier. Half wave rectifier. Same thing, and the efficiency of half wave rectifier is, it can convert the 6 voltage AC to 6 voltage DC only 40%. You will not have appropriate 6 voltage DC in the case of half wave rectifier. Only the 40% efficiency is there in the half wave rectifier. If I take two diodes in the same circuit, what will happen? If I take two diodes on the same circuit I have taken two diodes, and as I said, for the first positive half cycle, this point is positive, this point is negative. So the positive is connected to P type, negative is connected to P type. This is called, suppose I say this is D1 and now this is D2. So D2 is in non-conducting stage, D2 is in reverse bias, D1 is in forward bias. There won't be any current because of D2, but there will be current because of D1. So the output will be there because of D1. Or if I draw one more graph, so there is an output because of D1. And what will happen for the first negative half cycle? This is an AC, this is an input. What will happen for the first negative cycle? This is minus and this will be plus. Minus is connected to P type, this is in non-conducting stage or in reverse bias, but this have become into forward bias. At the end, across the load resistance, there will be a voltage. So because of the diode D2, so here again you will get an output because of D2, and again there will be an output because of D1, and again because of D2. So this is called as a full wave rectifier, and the efficiency of full wave rectifier is 80%. And in the case of full wave rectifier, this is not drawn this manner. The circuit will be little bit changed. I need to short this, and from the center tap of the secondary coil, I need to take a load resistance and connect in this manner. And across this load resistance, I need to collect an output. So the drawback of full wave rectifier, though the efficiency is 80%, the drawback is to get exactly the center tap of this secondary coil. Manually it's not possible if there is n number of windings, and that particular winding center point we need to take and connect this particular load resistance. So it is not practically possible. So you have a drawback with this particular full wave rectifier. That is the reason the next will be called as a bridge wave rectifier, where we will be using 4 diodes, and we will be avoiding this particular center tap and having 4 diodes and getting the same efficiency as 80%. So this is all about rectifier which converts alternating current to direct current. But even if you take a bridge wave rectifier, the output which is coming as an 80% 6 volt DC, it is again not in the form of pure DC form. It is called as in pulsating AC. Pulsating is it will be a mixture of little bit of AC and DC. So if you see in the market a less cost charger and high cost charger, this will be the difference. Less cost charger, it will not be having with filters. It will be pulsating form, little bit of AC is mixed into the output, which can damage your appliances like electronic gadgets or mobile phones. So to purify that, again we have to take a filters using a capacitance and inductance. So that output will be in the pure form of DC. Okay, चलो, thank you. अब क्या करना?